Hi everyone, please go through my previous videos for better understanding of this video. Coming back to our video, here we can see T1 is more than T2. What is T1? T1 is longitudinal relaxation time. T2 is transversal relaxation time. So we cannot just pinpoint exactly the end of longitudinal relaxation or transverse relaxation. So we can just tell, like, when you put a curve with time and longitudinal magnetation or time and transverse magnetation, this is a T1 curve, this is a T2 curve. As we cannot pinpoint exactly the end of longitudinal relaxation or transverse relaxation, here we can tell it as time when 63% of the original longitudinal magnetation was reached. Here this is something like time when transverse magnetions decreased to 37% of the original value. So T1 is always more than T2. Just remember that. 1 by T1 is something like longitudinal relaxation rate. 1 by T2 is something like transversal relaxation rate. So we have protons which are randomly oriented. When this part is kept in a magnetic field, some protons align parallel, some align anti-parallel. Now we are giving a radio frequency pulse, and these are precising protons. So few of the protons take up the energy and they go into a higher energy state. When this process occurs, when will these protons take up the energy? Only when the frequency of this radio frequency pulse and this precising proton is same. Then only this precising protons, they take up the energy and go to the higher energy level. That's what is written here. Radio frequency pulse and protons have the same frequency. Then only these protons can pick up some energy from the radio wave. So what does this radio frequency pulse does? The purpose of this radio frequency pulse is to disturb the protons which are peacefully precising in the alignment with the external magnetic field. So how do you know the frequency of these protons? Lamar equation gives us the necessary frequency of the radio frequency pulse to send in. Got it? So this one you understood. Now what happens when the radio frequency pulse is switched off? So we'll take an example. First is T1. So normally this T1 is influenced by composition, structure and surroundings. So this T1 is influenced by composition of a tissue, structure of a tissue and surroundings. So we have an RF pulse which is switched off. So normally before RF pulse, few of the protons, they take up the energy, go to the higher energy level. When this RF pulse is switched off, these protons, they lose the energy and they go back to their lower energy state. When they are going back to the lower energy state, they release the energy into the surrounding. This is called lattice. So we have a precising protons, we have a lattice, right? Normally radio frequency pulse is switched off. These protons lose their energy and go back to the lower energy state. This energy is released in the surroundings called lattice. This precising proton, they have a magnetic field. Even this lattice surrounding, they have a magnetic field. So this magnetic field, it constantly changes in direction and it fluctuates according to the Lamar frequency. Remember this. This magnetic field constantly changes direction and fluctuates along to the Lamar frequency. Normally this precising protons is there, this lattice is there. Where the radio frequency pulse is switched off, these protons, they have to lose their energy and this energy and go to the lower energy level by releasing the energy into the surroundings called lattice. When this process occurs, it doesn't occur like simply it doesn't occur. This occurs when fluctuations of the magnetic field in the lattice occur with the frequency that is near to the Lamar frequency. Then only it can hand over the energy and relax. Now we'll have an example. We have precising protons, we have a lattice. Normally they hand over the energy to the surrounding, that is lattice, to relax. So here the example is water. In this process it is very difficult. This precising protons, it takes time for them to hand over the energy to the lattice. This process is more. That's why for water T1 is long. T1 is long. Water has long T1. So this process occurs. It takes time for the protons to lose their energy and go back to the lower energy state. Why this process occurs? It takes time for this process to occur in water. to hand over the energy and relax. Why? As the water molecules move too rapidly. The water molecules, they move too rapidly. So as we told, their frequency should be same. When they move too rapidly, it is very difficult for these precessing protons to lose their energy and go back. That's why this process occurs very slowly, does not occur quickly and very slowly. Thus, it takes long time for the longitudinal magnetization to show up again. This means liquid water has long T1. So one more example is medium-sized particles. Inside of water, there is a medium-sized particles. There are more medium-sized particles. These particles, they move very slowly. They have a fluctuating magnetic fields which are same as that of the Lamar frequency of the precessing protons. So easily energy transfer occurs. That's why they have a T1 is short. Now coming to fat. Why fat has short? Fat has short T1. We have fat. Normally, the carbon bonds at the end of the fatty acids, they have a frequency same near to the Lamar frequency. That's why resulting in effective energy transfer. That's why fat has short T1. Nice, right? Now coming to Lamar equation. Lamar equation is something like precision frequency is equal to gyromagnetic ratio into magnetic field strength. Normally this precision frequency becomes higher when the magnetic field strength increases. So when the magnetic field strength increases, the precision frequency becomes higher. By equation only we can tell it. So normally, I told you, right? Normally they are in random fashion, these protons. When you kept in the magnetic field, they become parallel or anti-parallel to the magnetic field. So they move around in certain way. This movement is called as precision. So how fast the protons precise? This speed can be measured by precision frequency. How many times the protons precise per second? So if we have a stronger magnetic field, then the protons precise faster. So it's like precision frequency equal to magnetic field. If the magnetic field strength is more, the precision frequency also will be more. If there is a stronger magnetic field, the protons precise faster. So we have something like precessing protons, we have lattice. When they process these precessing protons, they precise faster. So as they precise faster, this problem in handling down the energy to the lattice. So here what happens when there is a strong magnetic field, this proton they precise faster. If they precise faster, transfer of energy, I mean like protons has to lose energy to go back when the radio frequency pulses decrease. The protons they go back to lower energy state by releasing energy, right? This process occur. It may be difficulty in doing this process with more slowly in the as this lattice has slowly fluctuating magnetic fields. That's why T1 is longer in stronger magnetic fields. Super, right? Very good. Then coming to what T1 is over, what influences T2? T2 relaxation comes when protons get out of phase. You have to go through my previous reports, otherwise previous videos, otherwise you'll not understand. What is T2, what is T2 relaxation, everything I explained. What is longitudinal magnetization, what is transverse magnetization. T2 relaxation comes when protons get out of phase. Why protons get out of phase, everything is explained there. So two causes. Inhomogeneities of the external magnetic field, inhomogeneities of the local magnetic field within the tissue. Two tissues, external magnetic field is there, local magnetic field within the tissue, there is inhomogeneities. The protons become out of phase. Example, water. Water has long T2. Remember, water has long T2. Why long T2? As water molecules move around very fast. I told you, right? They move very fast. The local magnetic field, coming to local magnetic field, they fluctuate fast. The kind of average each other out and no big difference in the internal magnetic field from place to place. So there is no big difference in the internal magnetic field from place to place. So no big difference in the magnetic field strength within the tissue. So protons stay in step, so they do not go out of phase. There is no much inhomogeneity. So protons stay in step for a long time before they dephase. So T2 is longer. Very good. So coming to impure liquids, so they containing very some large molecules. So bigger variations in the local magnetic fields. Larger molecules do not move around fast, so their local magnetic fields do not cancel each other out as much. So larger differences in the local magnetic field causes larger differences in the precision frequency. Protons get out of phase. So T1 is shorter. Thank you.